So in order for us to have a better understanding of this frame forwarding process, we really need to look at a much larger example so we can take a look at the different types of scenarios that we might face. So let's make sure we are all looking at step 1 right now. So we can see this topology. Look what we have. We have 2 switches in this topology, switch 1 and switch 2. We even have a router. That's our default gateway.
Now, Raymond, before we get too deep in this, I'm looking at, see like 99, 55, 44. What is that? What is that trying to indicate to us?
Well, those are numbers and letters, Dan, and what they're trying to indicate is our MAC addresses. That's what they are. They're representing the MAC address of these devices. So instead of us writing out all 12 values of a MAC address, that would just take up a lot of space on the screen. And just by utilizing these 2 digits, we still accomplish the same goal of showing you how our switches learn MAC addresses, how they forward or flood frames. So those are the MAC addresses here. We got everything from 11, 22, 33, you can see, and we even have AA and B. Over on the left-hand side, make sure you notice we got the MAC address tables for switch 1 and switch 2. We're going to populate those and we'll show you. So everything we've talked about so far has really geared us up for this point in our discussion. So make sure that you are looking at step 1. Why? Because we need to learn more about the frame forwarding process. We only have a basic understanding of it. We have to dive deeper now. We have to dive deeper and look at the different scenarios that we can face. So look at what we have here in this topology. We have 2 switches, switch 1 and switch 2. We have a router, that's our default gateway. A whole bunch of PCs, and Dan, I'm looking in the upper right-hand corner. What's that device we have here?
Well, the one that interconnects switch 1 and A and B. Well, let me give you some hints here, folks. So that's a device that populates or builds out a large collision domain, and it builds a half duplex medium for communication. So it's a shared environment. That's a layer 1 device. So what device have I spelled out for us? Raymond, what device is that?
Well, that's a hub, Dan. And we've included the hub here just so we can see the difference between the behavior of that hub and the behavior of our actual switches, so we can fully understand why switches are so important for our environments. So, folks, Dan used a term here a couple seconds ago, collision domain. It says it breaks out that environment. It's just one large collision domain. Well, let's ask you, folks, how many collision domains do we have total here? Count them up. We want you to be counting them.
And remember that other name for collision domain we talked about? The other name is an Ethernet segment. We'll use that terminology when we get into things like spanning tree protocol, so that's pretty good. So I'm stalling here, Raymond. We're trying to count the number of collision domains. We want to give people enough time to do that. And so, Raymond, what are we looking at here?
Well, we have to remember that every single port on a switch is going to be in its own collision domain. So if I look at switch 2 and I count up the links that I have connected to my actual switch, I see 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 on switch 2. If I look at switch 1, I have to be very careful. I have to make sure I don't double count that link that is connecting me up to switch 2. Don't double count that. That's still 1. So I still only have 8. Now let's count the other link that I have on switch 1 going out to my hub. That's a total of 9. So here we have 9 total collision domains.
And we get to see them here on step 2 visualized. Okay, so although our discussion is not really going to be focused on collision domains, it's good to review that. Oh, and Raymond, what cable would we use to connect up switch 1 to switch 2 in the world of unshielded twisted pair Ethernet?
That would be a crossover cable, Dan.
Cool. All right, so... But Raymond, we're here to talk about communication, and before we get too deep into communication, let's just try to explain one more thing here. We see MAC address tables, yes, but when we look at the MAC addresses that we're showing you, we're only giving you 2 digits. So we'll just talk about them as 2-digit hexadecimal values when we know, yes, they're 12 digits. 12 hexadecimal digits equals the 48 bits. But we're going to keep it nice and concise so that those MAC addresses don't completely crowd our field of view.
Now, Dan, if one switch learns MAC address, is it going to share what it learns with another switch in our environment?
Okay, this is a big deal. This is a really big deal. So Raymond's asking me, will switch 1 and 2 do some MAC address table advertisements or a signaling protocol between them? And the answer is absolutely no. Absolutely nowhere in any Ethernet environment is there going to be advertised MAC addresses or requested MAC addresses between two switches. You need to get that out of your head. So these switches are still going to go through the same fundamental stuff we just introduced to you, where the switches are going to be listening to MAC addresses that are seen as the source inside of the frames. That's all it's going to go on. Okay, so whenever you're thinking about how does a switch learn about this MAC address, there's one way it happens. Listening to the source MAC address of frames. So get any concept of a signaling protocol between these two switches out of your mind, and we're going to really explore how it actually happens.
So now's a really great time for us to take a look at an example. And the example we're going to look at is utilizing a DHCP discover message. Why? Well, let's think about our MAC address tables right now. They're empty. So let's say it's first thing in the morning. Everybody's arriving at work. We turn on our PCs. What's going to happen? I need an IP address. Let's go find a DHCP server. So what is a DHCP discover message? Is that a unicast or is it a broadcast?
We just talked about this, didn't we? But it's good to review it. In the DORA process of DHCP, the discover is a broadcast. It's a broadcast. Now, Raymond, where is our DHCP server? Where is our DHCP server?
Well, in this topology, our DHCP server is going to be the PC with the MAC address of 22. Take a look at that. It's off of switch 2, folks. We can see it right there. So what's going to happen now when switch 2 actually receives this frame? There's two things that have to happen. Let's talk about the first thing. And it's based on number 1 that we see on the right-hand side of the screen. If you haven't read that yet, read it now. Switches learn where MAC addresses are by looking at the source MAC address in a frame. We've talked about that. So, what's the first thing switch 2 is going to do? Let's learn about the MAC address of this frame we just received. And let's associate it with the port it just came in on.
So that's what we just saw. Anytime we see a frame from a new source, we associate it with that port that it came in on. So 99 is now married to switch 2's MAC address table. Notice a few things here. We still don't have an association of switch 1 and MAC address 99. In order for that to happen, we need some communication to occur. And, we've got that frame now. And on step 6, we've already mentioned that PC22 is our DHCP server, but I want you to think about now communication flow. We know this is broadcast, and specifically a DHCP discover. So do you think that the switch is intelligent enough to forward it just to the DHCP server over there? What do you think, folks? Is the switch going to send it to the DHCP server knowing, hey, this is a DHCP discover?
Wait a second, Dan. We have to think about the type of frame. What type of frame are we dealing with? Is it a unicast or is it a broadcast? Folks, we said DHCP discover was broadcast. Wait. So how does our switch deal with broadcast frames? That's important. Make sure you're looking at step 7. Step 7 is showing us that if we don't know the MAC address yet, we're going to have to flood it out. But let's think about it. We are a broadcast frame. We'll never, ever, ever know that MAC address. So what do? We flood it out all ports except the port it came in on. Flood it out. All ports except the port it came in on. That's an important concept. That happens with all broadcast traffic.
And we could also analyze it from a slightly different perspective as well. Raymond, what layer of the OSI model are these switches?
These are layer 2 switches.
Okay, so a layer 2 switch isn't really going to be able to delve into the goings-on of layer 3. The DHCP Discover offer, that's layer 3 activity. And it doesn't have that deep of an awareness of it. So using our understanding of the OSI model, we get a reconfirmation of what Raymond just said. Now, on step 8, we also see that switch 1 wants to know about MAC address 99, right? So switch 1 received that frame, that broadcast frame. Why? Because switch 2 pumped it out to all of its ports except the port that it came in on, including that connection over to switch 1. So now switch 1 associates MAC address 9, D9, with the port of gigabit 0/1. So even though it's not directly connected, switch 1 will associate that MAC address with the port that it came in on. Okay, so there's not really like a hop count or anything like that with the MAC address table. It just says it's downstream. It's out this port. If I want to send towards that MAC address, I shoot it out my local port and hope it's going in the right direction. Now, Raymond, it's still a broadcast frame. Switch 1 just received it. What is switch 1 going to do with that broadcast frame after it learns the MAC address?
Well, that's an important concept, Dan, right here. You said it's still a broadcast frame. We haven't changed it. Our switches aren't going to modify these frames. They're taking these frames and they're making forwarding decisions based on them. So we're not changing them in any way, shape, or form. So switch 1 received the same thing that switch 2 received. So it's still a broadcast frame. What do we do with broadcast frames? We flood them out all ports except the port they came in on. So in this case, it's going to go out fast Ethernet 0/24. Now, our good old friend, the hub, receives this particular frame now. And what does a hub do with that? Well, let's remind ourselves, a hub is just a layer 1 device. That's all it is. Layer 1 device. So it receives bits in and it spits bits out. That's all it's going to do. That's why we used to call them bit spitters. Bits come in, bits go out.
And Raymond taught us flooding, switches flood to all ports except the port that it came in on. Hubs flood bits to all ports except where those bits came in on. So it looks at it from a different perspective. It's not focused on frames, it's focused on bits. That's a protocol data unit of layer 1 of the OSI model. Now, Raymond, is this a good or a bad thing, the fact that this broadcast fanned out and hit everyone on this side of the router? Good or bad?
This is a great thing, Dan. You know, at first you look at it and you're like, oh, this is garbage. But this is our learning process. Right now that we know where 99 is, anybody who wants to send anything to 99, they could just send it directly and we'll forward things instead of flooding them at that point. So we have to go through this process until we learn about everybody. At first it doesn't look great, but you'll see here as we go through this, it actually is a pretty good process and it happens so fast.
Okay, well, we sent our DHCP Discover. This is going pretty slow, isn't it? Thankfully, networks are quite a bit faster than this. On step 10, what do we expect after the DHCP Discover hits the DHCP server? We do have one. Well, we're going to get an offer back. We're going to get an offer back saying, here's the IP address that I can lease up to you that is part of the pool that should be associated with the subnet that you're in. But long story short, it's a unicast offer. It's a unicast offer saying, here's what I'm ready to give to you. Now, this is really cool, Raymond. So the DHCP offer is going to come, and the switch is going to receive that frame, and it looks like the switch just learned about a new MAC address in its MAC address table.
Yeah, it would learn about the actual MAC address of that DHCP server now. If we take a look at that, the DHCP server has a MAC address of 22. Well, if we look at the MAC address table, it says 22 is now associated with Fast Ethernet 0/2. So this DHCP offer, which is a unicast frame that went back, that source MAC address field said 22. What would the destination MAC address field say? It would say 99, because that is the actual destination MAC address we're trying to send this offer to. So now switch 2 looks at the destination MAC address field and it sees 99. Now, make sure you're taking a look at that MAC address table, because in this case, switch 2 compares that MAC address and the destination MAC address field to its MAC address table and sees that 99 is out Fast Ethernet 0/6. So am I going to flood it? No, not at all. As we can see here, in step 10, we're directly forwarding it out Fast Ethernet 0/6 towards 99.
So Raymond began this discussion of the actual frame flow by saying, we just turned our computer on, got in that morning, like 7:30 in the morning, because we're early risers, turn our computer on, we get our IP address now, we just got it. What are we probably going to do? Probably going to have to do some things like log in information. Not only do I want an IP address, but I'm probably going to have to communicate to some server out there, or maybe I'm just surfing the web. So I would expect something that's going to occur very soon thereafter is wanting to talk outside of this LAN. And how do we talk outside of the LAN, folks? That's a big deal. If I'm trying to communicate to something outside of this space that we see, beyond the router is our intermediary to the rest of the world. What do? Well, I got to know the router's MAC address, right? Communication at layer 2 is always going to be based on the destination MAC address that I want to talk to. And I don't know the router's MAC address yet. I didn't get that. Okay, so Raymond, how do I get the MAC address of my default gateway, the router here?
That's going to require us to do an Arp request. We know the IP address of our default gateway. That was given to us by our DHCP server. So my Arp request says, if you have the MAC address associated with this IP address, please give me that MAC address. So that's what I'm doing here in step 11. I am sending out that Arp request for the MAC address of my DHCP server. But let's stop right here. And let's remind ourselves what type of communication an Arp request is. Is it unicast? Is it broadcast? Is it multicast? What is it? It's broadcast. It's broadcast. So now that we know what type of communication it is, we have an understanding, or we can determine ahead of time how our switch is actually going to behave now.
So what did Raymond just talk to you about? We walked through obtaining our IP address from DHCP discover and offer. We don't have the 4-step process, but we get the idea here, right? Then, now that we've got our IP address, we just came in the morning, we obtained our IP address, we probably want to communicate with something outside of our LAN. Raymond, when I communicate outside of the LAN, who do I need to discover? And what do I need to discover about them?
Well, we need to contact our default gateway, that exit point outside of our network. And in this case, that happens to be our router with a MAC address of EE. Do I know the IP address of my default gateway right now? Well, I hope so. I hope my DHCP server gave me that IP address. That's its job. So I do have my default gateway's IP address right now. But I'm missing something. And what am I missing right now, Dan, that's really important for me to actually communicate to that default gateway?
I'm missing the layer 2 address. So I know it's layer 3, but I need to figure out its layer 2 address, its MAC address specifically. I'm going to do an ARP request. Okay, so that's what this step is talking about, step 12, ARP request. So this is a broadcast. We've already talked about it. And we're trying to obtain the router's MAC address, but it's a broadcast. notice what happens. It's going to go everywhere. This is actually showing us the broadcast domain, a concept where it says, here's where broadcast will go. It's basically everywhere in this layer 2 environment, and it is not passed by routers. So if the router did happen to have other interfaces, it wouldn't go out. It wouldn't go out the other interfaces on the router. But I don't want you to make a judgment call. Just like we didn't want to make judgment calls about, good or bad here. Yes, that broadcast, that ARP request, is going everywhere. Over to environments like AA and BB, pretty disconnected from router E, right? Well, it's okay. Our goal of a broadcast is to get it to everybody, and we don't want to be too judgmental about this process, do we? Okay, so Raymond, step 12 done. What do we expect after the ARP request?
Well, the ARP request is saying, give me your MAC address if you have this IP address. So I expect the router to respond back with an actual ARP reply. And that is unicast. So it's going to have a source MAC address of EE. It's going to have a destination MAC address of 99. So it's unicast. It's a unicast. So switch 2 gets this unicast frame. What's it going to do? Well, folks, now it's going to learn about EE, which is out port gigabit 0/1 associated with its MAC address table, and then it's going to forward it out fast Ethernet 0/6 because the destination MAC address says 99. So as you can see, we said that the initial flooding process of these broadcasts, not very efficient, but look at the response traffic, how efficient that is directly from source to destination. So that's really what we want to look at now. We want to take a look at these tables and think about how quickly in the morning everybody getting their IP addresses from their DHCP server, maybe going out to the internet, how fast, Dan, could we have our MAC address tables populated?
Well, if you actually plugged in a protocol analyzer, it's a little shocking how chatty our computers are. And we're not trying to make judgments about operating systems. We used to do that. We now accept operating systems for what they are, pretty chatty overall. So you have a computer plugged in, it's going to be talking enough for your entire LAN and the switches in your LAN to know about where your MAC address is. So we're going to have fully populated MAC address tables that are where the switches are aware of all MAC addresses in the broadcast domain. Okay, that's just something that we would expect. And so we've done a little bit of discussion here already. We've now seen, okay, MAC addresses are accounting for everything. The MAC addresses are accounting for everything. These tables, switch 1, look at those entries. Looks like all the MAC addresses. Switch 2, arranged a little bit differently, because topologically it's differently, right? And remember what Raymond said also. Raymond said that we're not going to have a signaling protocol between the two switches. That's not how these were populated. It was populated through observation of traffic flow, through observation of received frames and the source MAC address following that you see here on screen.